you, Laurent. First, I would like to thank the organizer for inviting me. I'm really enjoying it. I've been requested to present data on animal studies. In fact, instead of upper airways, it will be focused on the larynx. So obviously, with non-invasive ventilation, there is the interposition of the laryngeal valve between the ventilator and the lungs. And so the question is the larynx always open during ventilator insufflations? Years ago, in the 80s and in the 90s, the team of Praud in Belgium, using endoscopic observations in adult humans, showed that there was an inspiratory glottal closure when increasing inspiratory volume or pressure during nasal intermittent positive pressure ventilation. And they concluded that laryngeal opening conditions the efficiency of alveolar ventilation. And they also suggested the following potential consequences: patient-ventilator asynchrony, alveolar hypoventilation, diversion of gas into the esophagus with the risk of gastric dilation and consequently of increasing gastro-esophageal reflux, and the risk of oral leaks. We've been studying neonatal lamb models since about 10 years now with regards to non-invasive ventilation. And you can see this chronically instrumented lamb model with many electrodes and probes, and to be able to perform polysomnographic recordings during non-invasive ventilation using now a servo-eye ventilator. And we're using a nasal mask. This is specifically designed and molded the plastic nasal mask for providing non-invasive ventilation for lambs. And this is a recording we obtained during our first studies about 10 years ago. So from top to bottom, you have the EMG of the glottal dilator muscle, the raw and integrated signal. You have the glottal constrictor muscle, diaphragm, mask pressure, tracheal pressure, lung volume. As you can see during inspiration, you can see this nice inspiratory burst of the diaphragm, and at the same time of a little beginning a bit before the diaphragm, you have this nice inspiratory activity of the glottal dilator muscle. And you can see there is, in this instance with the CPAP, there is no activity of the glottal constrictor muscle. This is quite different. During a pressure support, in this example at 10 centimeters of water, you can see here the plateau of mask pressure. You can see the inspiratory activity is much decreased. At the same time, no inspiratory activity of the glottal dilator, and you can see this nice inspiratory activity of the glottal constrictor. At the same time, if you look at the tracheal pressure and lung volume traces, you can see the plateau of these recordings. We can see that during pressure support, and we saw that also during non-invasive nasal volume control ventilation. And so we can we're able to show that there is a linear relationship between the amplitude of the glottal constrictor EMG and the laryngeal resistance, measured by two catheters, one in the trachea and one just above the vocal cords in the lambs. So we concluded in this first paper that active inspiratory laryngeal narrowing was frequent during nasal intermittent positive pressure ventilation with pressure support as well as in volume control mode. During non-REM sleep, especially during non-REM sleep and quiet wakefulness, but you have to understand that we are not able to get much REM sleep in our lambs during the experiments. And we also concluded that the higher the amplitude of glottal constrictor muscle EMG, the higher was the laryngeal resistance. This is the next paper we published on the involvement of mechanoreceptors. So physiological study to be able to know where was the origin of this reflex closure of the larynx against the insufflations of the ventilator during pressure support. And I don't have the time to provide all the details of the experiments, but we're able to conclude that This inspiratory glottal closure in pressure support originates from the stimulation of bronchopulmonary receptors, not from the upper airway and not from the chest wall receptors. We had lungs with isolated upper airways we could ventilate, lungs with tracheotomy, vagotomized and non-vagotomized. Recently, we were able also to show that the bronchopulmonary receptor, which are at the origin of this reflex activity of the larynx against the insufflation in pressure support, does not originate from the bronchopulmonary C fibers. You can see on these traces, this is again the glottal constrictor during the insufflation in lungs with intact C fibers and after C fiber blockade. On average, if you look at the percentage of respiratory cycle with inspiratory activity of the glottal constrictor, you can see the same percentage in the 8 lungs before and after C fiber blockade. Okay, now NAVA. The big question, obviously. This is recording we obtained in the same lab. So again, a CPAP 0, pressure support, and nasal NAVA. And as you can see, it was with the pressures were 4 centimeters of water for pressure support. No, excuse me, it was for this lab, it was around 20. And you can see about the same for the peak pressure in nasal NAVA. And as you can see, inspiratory activity of the glottal constrictor and no activity during NAVA. And we concluded that with nasal pressure support around 4 centimeters of water, inspiratory glottal constrictor EMG was observed in 3/4 of the lambs. And in NAVA, we never observed inspiratory glottal constrictor EMG. I have to tell you that it was only during 10 to 15 minutes at each level. It wasn't during several hours. And we are now doing experiments during a much longer time. So why do we don't have any inspiratory laryngeal closure in nasal NAVA? In this paper, we suggested that maybe it's because there is a kind of more physiological insufflation pattern in nasal NAVA compared to nasal pressure support. And especially we noticed that the inspiratory pressure rise time in nasal NAVA in our lambs was around 0.4 seconds. Versus the setting in pressure support we had in pressure support, which was 0.1 second. And we also had a question about arterial PCO2. We and others years ago have demonstrated that hypocapnia increases post-inspiratory glottal constrictor EMG. In a setting, in our experiments, hypocapnia was inconstant, however, somewhat more frequent in nasal pressure support than in nasal NAVA. But it was not necessary, hypocapnia was not necessary, and was not sufficient to see this inspiratory laryngeal closure. So this is the last paper which has just been accepted in a critical care medicine, where we tested the effect of inspiratory pressure rise time and the effect of hypocapnia. And I won't speak of hypoxia, just to tell you that hypoxia doesn't seem to have any constant effect on the laryngeal constriction during inspiration in pressure support. So these are experiments only in pressure support now. So here we tested the inspiratory pressure rise time, and as you can see on the upper graph, these are again the percentage of respiratory cycles with inspiratory activity of the glottal constrictor. Inspiratory rise time, 0.12, 0.05, 0.2, 0.12, no difference. And even if we increase the inspiratory rise time to 0.4 seconds, which is huge for a neonate. We don't have any decrease in the percentage of respiratory cycles with the inspiratory laryngeal constrictor activity. So no effect of altering the rise time of the inspiratory pressure. What about CO2? As you can see, this is again the percentage of respiratory cycles with inspiratory activity of the glottal constrictor. this is the PCO2. So this is baseline, nasal pressure support. Pressures are 15.4 centimeters of water. You can see this big amount, big percentage of, high percentage of cycles with the glottal constrictor activity. As soon you add a bit of CO2 in the inspiratory line of the ventilator to increase the PCO2 around 50 millimeters of mercury, in all lungs, you shut down this activity after, on average, 90 seconds. So in conclusion, active inspiratory glottal closure against ventilator insufflations are present during nasal pressure support and nasal volume control ventilation, is absent during nasal NAVA, appears to originate from bronchopulmonary receptors, but we still don't know if it originates from the rapidly or slowly adapting receptors, because we don't have any way to test that in non-sedated lambs. I have to underline also that all experiments are performed in healthy, full-term lambs in the first week of life, and allowing mild, moderate hypercapnia, but not increasing the inspiratory pressure rise time, inhibits laryngeal closure, which may be of clinical relevance. So if you want a bit, a few 2 or 3 slides on ongoing experiments in lambs. These are unpublished results, so please close your camera. Thanks. We are performing experiments on the various patterns of patient-ventilator interaction of laryngeal origin during nasal pressure support and nasal NAVA, as well as during nasal high-frequency oscillatory ventilation. You may know or not that this is non-invasive high-frequency oscillatory ventilation is being used by some teams in neonates. We are also studying gas insufflation into the esophagus during non-invasive ventilation, and we are assessing the effect of various modes of non-invasive ventilation on gastro-esophageal refluxes. So just a few slides to show you the various types of interaction we can have between the larynx and the ventilator. Here you can see on the mask pressure at the time of the beginning of the EMG of the glottal constrictor. You can see this small increase in pressure. So the closure of the larynx is at the beginning of the plateau, pressure plateau. You can see also that at the same time that there is a decrease in the flow, in fact. You can see that at times this closure can occur a bit later. And in fact, this is the most frequent pattern we could see. And in fact, we have been studying now lambs during 6 hours in nasal pressure support, again 15.4 centimeters of water, and in a very high percentage of the cycles, we can see what could be premature cycling of the ventilator due to a closure of the larynx. And at times, we're able also to see this burst of multiple auto-triggering at the time of central apnea with the tonic activity of the glottal constrictor. And this is very frequent in the neonatal lamb. These auto-triggerings may be or may not be specific to the servo-eye. I don't know. I'm not an intensivist, so I don't have this knowledge. Just to show you what kind of recording we get on, in our studies on gastro-esophageal reflux during non-invasive ventilation. We are studying, in fact, esophageal multi-channel intraluminal impedancemetry. And as you can see, so this is again during pressure support, and you can see maybe the premature cycling of the ventilator. And you can see here gastro-esophageal reflux, which is moving in the cephalad direction. And the last slide is about gas insufflation into the esophagus. And you can see this is in the other direction. And you can see that increase in impedance, which tells us that there is gas insufflation in the esophagus. And it is not, in this example, but it's not always the same. You can see that it is not with each insufflation. It's one insufflation over 2. With that, I thank you. I must acknowledge also all these persons who are doing the experiments, and collaborator, Jennifer Beck, who is in the assistance, also Dr. Nathalie Sanson, my research assistant, who is here also. And I must disclose that one servo eye is on loan from Mackay in our lab. Thank you so much.